the second part, we're going to explain how the roots of the equation of motion, the roots of this Laplace transform uh, will affect the damping ratio and natural frequency of the motion. Okay, this is also a revision for you. Now, let's say you have these two roots, okay, and this is a complex root. Okay, you have the real part, okay, which is in the x-axis, and the y-axis is the imaginary part. So your roots is the real part plus minus the imaginary. So imaginary root. Okay. Now the distance between the origin. Okay. You have before that you have the left half of the S plane and the right half of the S plane. Okay. So we know that um, from the previous courses that we have taken that the left side of the S plane is the stable, okay, system. Okay, the system will be stable, and the right side is where your system is unstable. Okay, so in this case we are looking at a stable system, right? All right. Now the distance between the origin to the roots, okay, is called natural frequency. The straight distance is omega n. Okay, so the natural frequency. The x part of it is represented by negative damping ratio times natural frequency. Okay. Now, um, the closer you get, okay, the closer you get to the origin, the time to half amplitude is increasing. What does that mean? Okay. If it's closer to the origin, of course your omega n will be smaller. Okay. It will be smaller. So if it's smaller, then you have the um, the the period, the time, okay, to halve the amplitude. It will take longer, okay, if it's closer, because your natural frequency is smaller. Okay. Now on the y, okay, okay, on the y-axis we have the imaginary part, and this y component of this omega n is known as the damped natural frequency, or simply the natural frequency, and that is equal to this equation, omega n times square root of 1 minus the ratio squared. Okay, this is the actual natural frequency of the system. Okay, and the closer it is to the origin, the period of oscillation is increasing. The response will be slower. Okay, so if you want faster response, you must increase the undamped natural frequency, or simply increase the frequency lah. Okay. So how you increase the frequency? You can increase the imaginary part. Also, you can also increase the real part. Okay, any one of it. Okay, but if you just choose to increase the natural frequency by just increasing the imaginary part, okay, by just increasing the natural frequency of the system, you will have a larger angle. Now let's look at the angle. Now the angle, okay, from the natural frequency to the x-axis on the left side is theta. Okay, and this theta will define the value of damping ratio. Okay, theta is equal to the arc cosine of the damping ratio. So the larger the theta, the smaller is your damping ratio. So if you just decide to just increase the imaginary part of it, okay, because you want to have more frequency, okay, higher natural frequency, you want to have faster response, your theta will be big, huge, and if it's huge, your damping ratio will be small, and you may have a problem. You may have a problem. In fact, although your period of oscillation decreases, your time to half amplitude is increasing. So meaning that it will not settle juga lah, tak settle lah, lambat lah juga settle. Okay, so if you just decided to just have to increase the real part of it, so the real part of it, okay, so your time to half amplitude is reduced, which is good, but your period of oscillation will increase, because your damp natural frequency is smaller because of your damping ratio is a lot higher. It's higher lah. Okay. So you can just place the the, the roots. Okay, you need to place the root at exactly the right position to have a good uh, uh, response or good motion. So for aircraft longitudinal motion, it will behave like this. Okay, be it phugoid or short period oscillation. Okay, the, the good and the bad motion will be determined by the location of the roots. Okay, so for okay. So this is the standard characteristic equation, and this is the roots of the characteristic equation. Will look something like this. Okay, and this is the x. Okay, the real part, and this is the imaginary part that we have been discussing just now. Okay, and now if you look on the left hand side, okay, left side of this is a stable region. Okay, so if you have two roots here, then you are talking about the damping ratio, okay, larger than 1. If your root is here, okay, we have a pair of roots here, then this is damping ratio equal to 1. If it falls somewhere along this, okay, dash line on the left, it will be under damped, okay, between 0 to 1. But if it's here, the damping ratio is 0. So this is undamped. Can it go to the right? Yes, it can go to the right. Okay, if the system is unstable, so the damping ratio will be between 0 to -1. If it's here, okay, if it's here, to 0 to -1. Uh, so if this under damp part 0 to 1, you will have an oscillation, but it is decaying exponentially. On this side, on the right side, you have oscillation also, but it is not decaying. In fact, it is diverging. It is increasing in amplitude. Okay. Uh, again, okay, exponentially. Okay. And if it's critical or over damped, okay, over damped condition, but on the right side, okay, where your damping ratio is equal or larger than 1, it will exponentially increasing, okay, the amplitude. Okay, so that's the difference between the left and the right side. So the left side, it will be decreasing or will converge to 0 exponentially, but on the right side or the unstable part, it will diverge. Okay, it will increase exponentially. Okay, so that is about the second order differential equation. So these are the table that tells you how the types of root, okay, the magnitude of the damping ratio, the type of roots, and the time response. Okay, time response. Okay. Next up, we'll go for pure pitching motion.